Good evening. Good afternoon from Madrid. It's 3 p.m. Here right now. Okay, and we are about to start this second AST session. Okay, on mutation testing and debugging. Okay, we have two full papers and a short paper in this session. So the first paper is titled "Mutation Testing Strategy for Solidity Smart Contracts." Okay, and the presenter is Morena Barboni from the National Research Council, CNR, in Italy. Okay, so you have the stage when you want.
So welcome everyone, I'm Morena Barboni, and I'm here to show you a work that was carried out by me, Professor Andrea Polini, and Andrea Morichetta from the University of Camerino. So the main objective of this work is to propose a novel mutation testing strategy for the Solidity language and to perform a preliminary validation of the approach. To this end, we implemented our strategy in the Sumo framework, which is a mutation of Solidity mutator. And then we performed a full mutation testing run on a set of real-world Ethereum applications. So first I will give you an overview of the mutation testing technique and of its relevance in the smart contract development field. Then I will introduce our mutation testing strategy and in particular which mutation operators we decided to include in Sumo. So after some details about the implementation of the tool, I will conclude the presentation with a discussion of the experimental results. So mutation testing is a powerful fault-based testing technique in which certain elements of the target program are modified in order to simulate typical programming faults. And the main goal of this fault injection process is to evaluate the adequacy of a given test suite and to guide its detecting real-world faults. So the core element of mutation testing is a set of fault injection rules called mutation operators. Each operator specifies how the code of the original program should be modified in order to generate a set of faulty programs called mutants. A mutant is almost identical to the original program, however it contains a very small change that mimics a typical programming fault introduced by a competent programmer. During a typical mutation testing process, the original test suite is run on each previously generated mutant in order to evaluate its fault detection capabilities. So if the test cases are good enough to detect the mutation, we see that the mutant has been killed. And the higher the mutation score, the more confidence we can have in the quality of our testing. On the other hand, the mutants that survive testing can provide useful insights about the main weaknesses of our so that we can craft additional test cases or improve the existing ones. So a mutation testing approach can be particularly relevant in the context of blockchain development. In fact, smart contracts are programs that must comply with very high reliability standards because the underlying execution model does not allow to revert any faulty or malicious transaction. Moreover, some reviews show that smart contract developers find it particularly challenging to deliver safe smart contract code. And this complexity is mainly caused by the peculiarities of the underlying distributed environment, such as the presence of complex interactions among cooperating smart contracts. So providing an effective mutation testing tool can help the developer to assess the quality of their testing activities and to deliver more reliable Ethereum applications. So during our research, we found 5 main tools that mutate the Solidity language. However, most of these tools are very limited model, which is the collection of fault types implied by all the mutation operators. So clearly using a limited set of operators can help to reduce the cost associated to the mutation testing technique. However, it can also compromise the quality of the final test suite. So our main goal is to design a comprehensive set of mutation operators which is capable of managing contract code while having the lowest impact possible on the computational cost and the manual effort required to the tester. So strategy. In the default model for Sumo, we started by evaluation of existing approaches and tools, which take both Solidity and more traditional languages such as Java. And this initial step allowed us to assess the strengths and the limitations of existing operators, like the generation rate of invalid mutants. Then we performed an extensive study of the latest Solidity documentation to obtain a classification of the main language features and, most importantly, to identify likely programming errors made by smart developers. As a result, we were also able to identify some opportunities for defining applications. As a last step, we analyzed several taxonomies of faults and vulnerabilities to make sure that our operators can inject meaningful and concrete mutations into the smart contract code. For instance, we consider the SWC registry, which is a project that provides a classification of known security issues in smart contract systems. So, as introduced earlier, mutation testing is a rather expensive. In fact, it might generate hundreds of mutants, must be tested and possibly manually analyzed to gather useful information. So, to encourage the usage of Sumo in a real development scenario, we try to introduce some cost reduction mechanism. The first solution that we adopt is limiting the number of stillborn mutants generated by Sumo. Stillborns are a specific type of mutants that are always killed by the compiler. So they introduce a performance overhead without actually playing a role in the test suite assessment. So to limit their generation, we combine selective mutation techniques and precondition checks which are applied during the mutant generation phase. A very similar approach is also used for limiting the generation of those mutants that provide redundant information about the test suite. And lastly, Sumo offers the possibility of fully customizing the mutation process so that the tester can select which mutation operators to apply and which contracts depending on the context. So currently, Sumo implements a set of 14 mutation operators. These are classified into general operators which target more traditional aspects of the language and Solidity-specific operators which, on the other hand, target the peculiarities of the Solidity language. So one of the main contributions of Sumo is the introduction of some novel operators which were never used for mutating contracts, are somehow enhanced from previous versions. In particular, Sumo introduces 7 operators which target a wide variety of Solidity features like blockchain properties and function modifiers, plus 4 traditional operators which target the smart contract overloading mechanism, enum types and conversions. So since I cannot describe how each operator works in detail, I'm going to show you a couple of examples. So this is a novel mutation operator that targets one of the most popular libraries among smart contract developers, which is SafeMath. In fact, the functions by this library help to protect a smart contract from overflow conditions during simple arithmetic operations. So this mutation operator is able to inject an arithmetic fault into the contract by swapping different instances of SafeMath function calls. So the SF is one of the most relevant global functions in Solidity, which is self-destruct. So let's suppose that the developer accidentally deploys a faulty smart contract on the blockchain. Because of code immutability, the only solution is to actually delete the contract before this fault can manifest in some critical failure. However, if the self-destruct mechanism is faulty as well, then it won't be possible to remove the contract. The SFD operator helps to scenario because it forces the developer to define a dedicated test case that ensures the proper destruction of the smart contract. first example, the CCD operator removes the user-defined constructor from the contract to simulate the improper initialization of the state variables. So the only way to kill this type of mutant is by ensuring that the contract is properly set up before its actual deployment. So now we'll give you some details about the implementation of our tool. Sumo is a Node.js application that you can currently find on GitHub. Sumo uses the Solidity parser handler module for parsing and visiting the syntax of the contracts that must be mutated. During the mutation testing process, Sumo interacts with an underlying testing framework such as Truffle for compiling and then testing the mutants, which are usually deployed on a local blockchain test network by means of Ganache. So the architecture of Sumo consists of three main modules. The mutation runner responds to orchestrating the whole testing process. The mutation generator controls the execution of the mutation operator and therefore the mutants, while the reporter provides functionalities to the tester. This mutation testing process performed by Sumo. When the user starts a new test, the mutation runner generates the syntax tree of the contracts that must be mutated. Then the mutation generator runs all the mutation operators previously enabled. Each operator visits a specific tree and applies mutations according to its rules. So once the mutants are ready, the mutation runner tries to compile and kill each mutant by running the provided test suite. And at the end of the testing process, the reporter provides a final test report to the user, as well as a copy of each valid mutant generated by Sumo. So, in order to validate the efficacy of our approach, we performed a complete mutation testing run on two open source Solidity projects. We Ether crowdfunding, which is an application organizing campaigns. Event is an application that allows a user to organize events or buying and selling event tickets. So these two applications represent a good starting point for the validation of Sumo, because they meet a good variety of programming features, and most importantly, their test suites achieve quite good levels of coverage, meaning that we can further investigate the relation between coverage metrics and the mutation score. So the experimental results show that the selected applications achieve quite low mutation scores, meaning that a large amount of mutants actually survive at testing. This suggests that real-world high-coverage test suites cannot guarantee the reliability of a smart contract application. Moreover, we can also see that the mutation score is particularly low in the case of Solidity mutants. For instance, the Ether crowdfunding was only able to kill around 29% of the generated Solidity mutants. So this result confirms that addressing the peculiarities of the Solidity language can be particularly challenging for smart contract developers, which also underlines the importance of dedicated operators. Lastly, we can see that Sumo generated a relatively low percentage of stillborn mutants, which can help to reduce the overall cost for evaluating a given test suite. So to further understand what's the actual usability of Sumo real development scenario, we analyzed the live mutants generated for the Bionic event application, and then we used this feedback to further improve the fault detection capabilities of its test suite. As you can see from these two tables, this mutation analysis process allowed us to significantly improve the mutation score associated to by the test suite. particular, analyzing the light mutants allowed us to improve the existing test data and also to identify and correct some issues present in the contract under test. So, in conclusion, we can say that mutation score is a more reliable indicator of activity quality, and that a mutation testing approach can particularly benefit business-critical programs like smart contracts. Moreover, the preliminary validation of Sumo provided encouraging results, both in relation to injected by our operators and to the feasibility of the analysis process. Clearly, we need to perform a more extensive of the tool. However, these initial findings suggest that Sumo can help smart contract developers to write higher quality tests to deliver more reliable solidity applications. So our to-do list for the future includes several tasks. However, right now we are mainly the validation activity to a larger set of more complex applications, so that we can derive a more solid answer on the effectiveness of our approach. Of course, we also want to understand to what degree the novel mutations contribute to the overall efficacy of the strategy. Another important activity on our list is analyzing performance and scalability aspects, so that we can better understand the actual usability in a real development setting. And lastly, we aim to improve the overall of the tool, starting from providing a more user-friendly graphical interface. Thank you for your attention.
For your presentation. Okay, remember that you can write the questions in the chat. Okay, in the meanwhile, let me ask you some questions. When you presented the table with the mutation scores for those two applications, okay, I noticed that you said all, okay, and solidity, but does the solidity mutation operators are included also in all?
Yes, they are included.
Include both. Okay,
yes.
So include also the solidity operators. And I have another question, because you said, okay, with a bionic application, we just design a new test cases. Okay, did you propose those test cases to the project, because those are open source projects? Yeah. Right, so I guess you can provide those tests, okay, to the authors of the project so that they can.
No, we haven't done that, but yes, maybe we will do that in the future.
Mm-hmm. Okay, we have a question in the chat. Xavier says, "Thank you for the great talk. When improving the test suites after the mutation analysis, what were the most common fixes you had to apply to the existing tests? For instance, creating new tests, refining assumptions, etc." Very interesting question.
Well, in general, we had to add some additional test cases, because there were for instance, some methods within the contract that were never exercised by the test suite. And we also observed that, for instance, there was a method which included a modifier which specified who could access that specific method. And in particular, in that case, that method was only accessible from the owner. And we observed that the test cases did not consider the unhappy path scenario. So, for instance, they only tried to test the positive scenario in which the method was accessed by an unauthorized account. So, for instance, in that case, we enhanced the test so that we could also consider a scenario in which an unauthorized user attempts to call the method. Apart from that, we also found some faults in the existing test cases. For instance, there was a contract that contained some nested require statements, which are some statements that act as guard mechanism. So they check on some preconditions, and then if the condition is respected, the transaction can be carried out. Otherwise, the transaction is reverted. And we saw that in such a case, the developer got a bit confused. In fact, in a couple of tests, they were exercising the wrong require statement within the contract. And this was particularly interesting because it's a fault that might be a bit difficult to find within a test suite. So this was particularly useful.
Thank you. Yeah, Xavier corrected me. Okay, it's refining assertions, not assumptions. So, any other questions? If not, I have just another more technical one, which is if the tool you developed, okay, needs because I'm brand new in this smart contract world, okay. So if I need to set up a smart contract infrastructure, okay, or does the tool already set up that for me, or specific needs for that?
Basically, the tool interacts only with the testing framework. So, for instance, if you have your configuration file, then Sumo automatically, when it interacts with your, for instance, with your Truffle framework, your framework will automatically use that configuration file. However, in the case of your local blockchain test network, well, that is entirely up to the tester. So the tester has to set up its own blockchain instance to deploy the contract.
Okay, so the test framework basically recognizes that it needs this infrastructure and it will set up it for you, right? Okay, thank you. Any other questions from the audience? Okay, so thank you very much, Morena, for your presentation. Okay, and just remember that when this paper ends, sorry, there is another question from Alejandra. Did you have anyone apart from your group using the tool? They give you any feedback on usability? So we have time for this question. So
no, not really.
Indeed, in line with what Alejandra was saying, that was one of the purposes of my previous question on if whether you proposed your new test cases, okay, for the project, right? Because I mean, it could raise knowledge about your tool, okay, and I think it might be interesting because indeed I was a bit surprised when reading the paper that there was such a lack of this things, okay, within the blockchain world, okay, where usually, okay, you are building safe transactions on top of that, okay, and it was quite surprising that with the mutation operators, okay, based on Solidity, you were able to find such a big gap, okay, of things that could be solved or fixed, you know, within those tests. Any other question? Okay, so let me thank Morena for the presentation, and remember that if you want to ask some more questions when this session ends in, well, not the session, but the paper in 6 minutes, okay, she will be transferred to a discussion room and you can join the room, okay, a pop-up will appear on the chat, okay, so that you can join the room and ask any other questions if you have any. Okay, I will leave you here and I will join the backstage for the next paper to see if everything is ready. Right, see you in 5 minutes. Thank you, Morena.